All right, friends, so in order to find the inverse function here, we first want to replace with f of x with y. Okay, and at this point we can either isolate for x or we can swap x and y or invert them. And I'm actually going to choose to invert x and y at this point. So this here is the process of finding the inverse. So I'm replacing y with x, I'm replacing x with y, and now I'm going to re-isolate for y. And again, you could just solve this for x and then do the swap later. So from here, I'm going to add 1 to both sides. So I have x plus 1 equals 3y, and then I'm going to divide each side by 3. So I have y equals x plus 1 over 3. And what I want you to notice here is that not only are the operations inverted, but their order is also inverted. So here we multiply, then subtract. So if we want to do those, if we want to invert that, we would first have to undo the subtraction with addition and then undo the multiplication with division. So again, here with the original function, we have multiply, then subtract. Here we have add, then divide. Now we want to be clear at this point that we have found the inverse of f of x, so we're replacing this y with our inverse function notation. And that clearly identifies this function as being the inverse of f of x. So go ahead and try yours. And then after you've tried yours and checked it, go ahead and take a minute and read through this. And there's sort of this idea about, how can we tell if a function is going to have an inverse that is also a function? And if it's not, how do we restrict the domain so that its inverse is also a function? And we'll do that in the next example. So for problem number 3, we are asked to find the inverse of this quadratic function, but you'll notice that the domain has been restricted for this inverse, and that's important because this way when we graph just this portion, we ensure that the inverse of this portion is also a function. Because if we were just to invert this here, we'd have like a sideways parabola, and that is not a function. So by limiting the domain here, when we now take the inverse of just the solid piece of this quadratic function, that new function, that inverse function, will also be indeed a function, not just a graph. So here I have some points. These aren't all they didn't all fit on the paper, but they fit close enough. So if I'm going to graph the inverse, I can actually write the inverse function, or I could just plot those points inverted. So treat this as 8, -2. So what I'm going to do here is I'm going to plot these 3 points here. -1, 5 is now going to be 5, -1. Actually, I'm not going to do that because I just, again, am reminding myself and you that our domain's restricted. So we're starting with that 0, 4. So we're going to plot 4, 0. We're going to plot 1, 5 as 5, 1. And 2, 8, when we invert the coordinates, is now over 8 up 2. So when I do that, we get this function here, which is a square root function, okay? So we have the inverse function graphed here. We have the original function graphed here just for its restricted domain. And if I want to find what the actual inverse function is, I'm going to replace f of x with y. I'm going to invert x and y. And I'm going to solve for y. So I'm first going to subtract 4 from each side, and then I'm going to take the square root of each side. Now, the reason I didn't put my plus or minus here is because I'm only inverting the portion here for which I have non-negative input values. So that restriction is going to hold true when I find the domain when I find the inverse as well. So this square root function, which you can see has a translation to the right 4, is the inverse of this portion of the original quadratic function. So you're going to do the same thing with yours right here. I'll pause the video, I'll fill it in, and then I'll unpause it so you can check your work. So you might remember from last year that we know that a function we'll have an inverse that is also a function if that function, if the original function passes the horizontal line test. So in other words, if a function starts being a one-to-one, so for example, this cubic is a one-to-one function, every x has one y and all of those y's are unique. Its inverse is going to be a function. Here we have a quadratic function, which is definitely a function, but it's not one-to-one. And what I'm saying is 1 to 1. It's not one-to-one because two different x values here yield the same output. So it does not pass the horizontal line test, which does not prevent it from being a function, but it prevents its inverse from being a function. That's why if I'm trying to find an inverse function, and that inverse function is, it has to be a function itself, that we have to restrict the domain of the original function to guarantee that its inverse is also a function. So I'm going to go ahead here to my fourth example, and it gives me a function. It asks me to determine whether the inverse is a function and then to find it. So what I want to think about is this function a one-to-one function? Okay, so if I were to graph this function, it's a cubic. And this cubic is written so that I can identify the transformations. It is shifted up 1 unit. It's definitely going to have that N shape with a flexion point, and it has a vertical stretch of 2. Now that doesn't affect at all whether or not this function is one-to-one. So whether the inverse is a function, yes, because f of x passes the HLT, okay? And it already passed the vertical line test, otherwise we couldn't have identified it as a function. Now when I find the inverse, I'm going to replace f of x with y, then swap x and y, and now solve for y. So when I do this, I'll have y cubed I'm going to subtract 1 from each side and divide by 2. And then I will take the cubed root of each side, okay? So when I do this, I'll have a cubed root function, which when I graph it is going to look like the reflection of this line over the line y equals x. So it's going to look roughly like this. So it's a cubed root function. So this is the inverse, the inverse function is the cubed root of x minus 1 over 2. And that's all being cube rooted. And of course we could rationalize that denominator a little bit. I'm not going to worry about that right now. Here's f of x, here's the inverse f of x. And you can go ahead and do your example now. Got a little ahead of myself. Here's the answer to number 4. For the student example, and then I just started my 5th example and forgot to push record. So let me talk you through this. I've gone ahead and replaced f of x with y, and then gone ahead and found the inverse by swapping x and y. I need to rewrite this so that y is isolated, but in order to do that, I need to first divide each side by 2, okay? And then I'm going to have to square each side. The problem with squaring is that I'm introducing an opportunity for points in the inverse here that don't have points of origin in this original function. So what that means is I'm going to have x squared over 4, right? Because I'm squaring this whole fraction equals y minus 3. And then I'm going to have y equals x squared over 4 plus 3. Now the problem is if I think about this original function, this function is shifted to the right 3 units and also has a stretch of 2. Okay, so this guy is restricted, my domain is restricted to values that are greater than or equal to 3. When I invert it, I'm going to get something that looks like this, okay? And that means that I am restricted to values for which x is greater than or equal to 0, okay? So again, I need to make this sort of prediction about what's the domain restriction here, what's the domain restriction here. So I can sort of say that this is the inverse function, but it is only true when x is greater than or equal to 0. So I'm restricting the domain of the inverse, or I could restrict the domain of the original function here to values that are greater than or equal to 3, and then sort of work from there. But hopefully you can kind of see it on this BB sketch over here that this is restricted to values 3 and greater. This is restricted to values of 0 or greater, which happens to be where y is 3, right? Because we've inverted them. So again, try yours, and then we'll do the last example. All right, so I'm going to do my last one here, and in order to set this one up for you, I have to introduce you to this kind of cool idea that because inverses include inverse operations in the reverse order, if you compose them, if you were to do here f of x of g, or f of g of x or g of f of x, that basically everything that's done here should cancel with everything that's done here, and everything will get stripped away with the exception of the input. So I'll show you what that looks like here. So f of x is 3x minus 1, and g of x is x plus 1 over 3. Now we can just look at this and go, oh yeah, those are inverses. This says times 3 minus 1. This says plus 1 divided by 3. So we have the inverse operations in the reverse order. But I can verify that by first taking g of f of x and asking, does that equal x? And then if it does, I can test it the other way, g of f of x, and verifying or asking, does that equal x? And if it passes both of these, then they are indeed inverse functions. If it fails the first, there's no reason to check the second. So I'm first going to find f of g of x by taking f of x and replacing the input with the g of x function. And what you'll see happens is those cancel. I'm left with x plus 1 minus 1. Those cancel, and I am left with x. So again, that was f of g of x. If I try g of f of x, something similar happens. So I'm taking my g of x function, which is x plus 1 over 3, and I am replacing the input, the x, with 3x minus 1. And when I do this, again, those will cancel. I'll have 3x over 3, and when I clean that up, I also have x. So because both compositions yielded x's in either direction, they are inverse functions. I have proven that by doing the composition. So you're going to go ahead and do the same thing with yours. Do the composition both ways to verify that they're inverses. And then I will unpause the video so you can see the work.